Okay, let's start part two by working some more problems with centripetal force. The next problem is problem number 27. Problem number 27 states, what is the radius of a bobsled turn banked at 75 degrees and taken at 30 meters per second, assuming it's ideally banked? Okay, in order to do this, you need to look in the book on page 199, because in the book they did a calculation looking at ideal banking. And what they said is that in a situation of ideal banking, the tangent of the angle of bank is equal to v squared over rg. Now, if it's important to you to understand where they got this, I'm not going to go over this right now, but this would be a formula you want to remember, because we'll be talking from time to time about ideal banks. And so by using this formula, we can calculate or solve this formula for r and find the radius of the curve. So that means that tangent of theta times rg is equal to v squared. And so that means that the radius we're looking for here is going to be equal to the v squared divided by g times the tangent of theta. So now let's put the numbers in. That's going to equal, and v was 30 meters per second squared, divided by 9.8 times the tangent of 75 degrees. And if you do the math here, you get a radius of 24.3 meters, 0.6 meters, as the radius of the circle. The second question is calculate the centripetal acceleration. Well, the centripetal acceleration is equal to v squared over r, which is equal to 30.0 squared divided by 24.6. So that's 900 divided by 24.6, which equals 36.6 meters per second squared. And then the last part of the problem, part C, does this acceleration seem large to you? Well, if you look at this number, 36.6, and divide that by 9.8, that comes out to be about 3.73 G. And I don't know, people can tolerate reasonably well at least up to 5G. And some people can tolerate, 7, 8, even 10G. And so this you'll feel this for sure, but this is not an unreasonable amount. And that's sort of how you answer that question as far as whether it's unreasonable or not. Number 29, you have a large centrifuge like the one shown in figure 6.37a. It's used to expose aspiring astronauts to the acceleration similar to those experienced in rocket launches and atmospheric reentries. I've heard this is called the vomit comet by some people because it does make some of the people that ride in it sick. So the part A of the question says, at what angular velocity is the centripetal acceleration 10g if the rider is 15 meters from the center of rotation? Okay, the way to figure that is to say that the centripetal acceleration is equal to the radius times the square of the angular acceleration. So that means the angular acceleration is going to equal the square root of AC over R. And we said that this is 10G, so that's 10 times 9.8, so that's going to be 98.0 divided by 15, which is the radius, and the square root of that. So the angular velocity, is 2.56 radians per second. The second part of the question is the rider's cage hangs on a pivot at the end of the arm, allowing it to swing outward during the rotation as shown in the second part of the diagram. What is the angle, theta, below the horizontal will the cage hang when the centripetal acceleration is 10g? So the first thing, you know that the weight, Fw, in the diagram you're looking at, is going to equal mg. And you know that Fc is going to equal mv squared over r. Now the trick is you have to see that the tangent of the angle is equal to mg over 10 mg, because they tell you it's 10g, so the tangent's 1 over 10. And if you do that calculation, that means that theta is equal to 5.71 degrees. The last part of it, and so 5.71 degrees. And they drew the free body diagram. They made it pretty easy by doing the drawing for you. The next problem is problem number 31. And problem number 31 is a problem I really like, so I would make sure you understand how this works. It says modern roller coasters have vertical loops like the one shown in figure 638. The radius of curvature is smaller at the top than at the sides, so that the downward centripetal acceleration at the top will be greater than the acceleration due to gravity, keeping the passengers firmly pressed into their seats. At what is the speed of the roller coaster at the top of the loop if the radius of curvature is 15 meters and the downward acceleration is 1.5 g? And so A is going to be 1.5 times 9.8, and the radius is 15.0 meters. So 1.5 times 9.8 is 14.7 meters per second squared. So we know that AC is equal to V squared over R. So that means that AC times R is equal to V squared. And so V is going to equal the square root of AC times R, which is 14.7 times 15. Now that looks surprisingly close to 15 squared, so it's going to be pretty close to that. So the velocity is 14.8 meters per second. Now we're going to move into a new section called Newton's Universal Laws of Gravitation. The key formula for Newton's Universal Laws of Gravitation is that F, which is the gravitational force, is equal to G, which is Newton's constant, times the mass of the first object times the mass of the second object over R squared. And G here equals 6.67 times 10 to the minus 11. So the first problem we're going to do, so these are the two keys you need to remember in doing these problems. There's actually one other, and that is the force due to gravity of any one large body is equal to G times that large body's mass divided by R squared. This is a situation where this second M is minuscule compared to big M. So that if you're talking about a person on a planet, the planet's big M is so huge that this has very little impact on the number. And so this is simplified to this formula right here. So let's look at problem number 34. It says calculate the acceleration due to gravity at the Earth due to the moon. Okay, so the acceleration due to gravity, by the moon is going to equal to big G times the mass of the moon divided by R squared, where R is the distance from the moon to the Earth. The numbers are 6.67 times 10 to the minus 11 times the mass of the moon is 1.99 times 10 to the 30, times 10 to the, got the wrong number here, I'm sorry. The mass of the moon is 7.35 times 10 to the 22nd kilograms, and that's divided by, these two are multiplied together, and that's divided by 3.84 times 10 to the 8th meters distance squared. And if you do the math here, you end up with the gravitational force due to the moon on the Earth is 3.32 times 10 to the minus 5 meters per second squared. So as we're sitting here, the moon exerts a very slight, tiny gravitational force on us, which is very slight and tiny, obviously, compared to the force of the Earth on us because of the difference in distance. The second part of the question is the same question: calculate the gravity on the Earth due to the sun. So it's the same calculation, but instead of the mass of the moon, you put the mass of the sun in, and instead of the distance to the moon, you put the distance of the sun in. If you put that in, you've got 6.67 times 10 to the minus 11. The mass of the sun is the 1.99 times 10 to the 30, and that's divided by a much larger distance, 1.5 times 10 to the 10th meter, 10 to the 11th meters, and that's squared. So that is going to be equal to 5.9 times 10 to the minus 3 meters per second squared. Now the biggest reason that this is so much, it's a factor of 100 difference, is this mass difference is much greater than the square of the distance difference. Now if you compare those two by dividing this number by this number, the effect of the sun is 178 times that of the moon. So what is asked the question, why do the tides, are they more affected by the moon rather than the sun? And it has to do with the fact that the moon is significantly closer than the sun is. It says the moon has a greater effect on the sides since it is the difference in the pull of the body on the near side of the Earth versus the far side. That is to say, you have one object on the near side and one object on the far side, and the moon's on one side when the sun is on the other side, and the Earth's diameter is much more significant in terms of the lunar distance compared to the solar distance. Okay, the next problem, problem number 36. Problem number 36 is very similar. It says calculate the acceleration due to gravity on the surface of the sun. And so we do the same kind of calculation. We're on the surface of the sun, so we're going to be, the distance we're going to be using is from the center of the sun to the surface of the sun, and that's the only difference in this calculation. It's the same numerator, 6.67 times 10 to the minus 11 times 1.99 times 10 to the 30, but now we're talking about the radius of the sun rather than the distance from the sun to the earth. So that's going to be 6.96 times 10 to the 8th meters squared. And so the gravity on the surface of the sun, if you could stand there, is going to equal 274 meters per second squared, which if we divide 9.8 into that, which is the second question, if you divide this number by 9.8, it's 28 times the gravitational force of the Earth. And which means on the sun, if you could stand on the sun and not get burnt to a crisp, you would weigh 28 times whatever you weigh on the Earth. So take your current weight and multiply by 28, and that's how much you would weigh on the sun.